So in this assignment, we are making an analogy of electron configuration and how these electrons might occupy what they call a hotel. So the first page goes over the Aufbau principle, which there's a more technical definition, but we'll just say you fill electrons from the lowest energy or the lowest floor in the hotel here first. So let's see if there are any violations. It says circle any electrons violating the Aufbau principle in these hotels. All right, and we're looking at Hotel A. There's a violation there. That electron should be down there. Okay, so that's a violation. Hotel B, again, that electron is a violation. It should be paired up in that 2p orbital. And then Hotel C, there are no violations. Doesn't look like. So wait, hold on. This is your 1s. It's your 2s. It's 2p, 3s, 3p. Okay, so there's no violation. That is good. Hotel C is looking good. Page 2 is going over the Pauli Exclusion Principle, which states that no two electrons in an atom can have the same set of quantum numbers. And the two implications of that is you can't have more than two electrons in an orbital. And the second one is if you have two electrons in an orbital, then they have to have opposite spins. Okay, so here it is. Opposite spins, and you can't have more than two. So let's see if there are any violations of this rule, Pauli's principle. Hotel A, here is a violation. Those two electrons would have the same set of quantum numbers. That one right there on the left, all right, will have n equals 2, L equals 1, which is the p orbital, and then m equals, or m sub l is equal to, we can call that the y-axis, right, or the +1 direction. +1 direction, let's say. You can say it's py. And then the spin, magnetic spin, is pointing up. Okay, and so that's also the same set of quantum numbers for that electron. So that violates Pauli's rule, which says you can't do that. So if this was spinning the other way, then the first three quantum numbers would be the same, but the last one would be different. So that would be okay, but it's not. Now over here, Hotel B, oh, looks good. That looks good. That looks good. I don't see a violation. Hotel B looks good. No violations in that hotel. That's the hotel you want to be in. Now Hotel C, let's see. Oh, there it is. Anything else? All right, so there's the violation there. Same reason. Those two electrons have the same set of quantum numbers. Okay, let's keep moving on. This is a reference. Okay, so it's just this reference, figure 1, is laying out the hotel in terms of floors or energy levels. All right, so you have your first quantum number here. All right, n equals. You have your second quantum number here. The layout is the shapes of the orbitals, the sp, df. And then you have your third quantum number is your orientations of each room. So just to recap, L is equal to 0. All right, integers starting at 0 all the way through, n minus 1. If n is equal to 4, this is your L is equal to 1. I'm sorry, L is equal to 0. That's your s orbital. All right, p is equal to 1. That's your p orbital. D is equal to 2. And then n minus 1, that's 4 minus 1, is 3. So F orbitals are your L equals 3. Then your orientation quantum number, your m sub L, is going to be all integer values starting from negative L to positive L. Okay, so just using here, this is an example. All right, let's just do this last one. All right, so if L is equal to 3, then you have negative 3. Well, it tells you right here, negative 3, negative 2, negative 1, 0, 1, 2, 3. So you have 7 different orientations of the F orbitals. All right, anyway, that's just a reference for you to use. And this is the same thing, just it's by energy levels. This is the Aufbau principle, which says you've got to fill, just like you fill protons to make different elements by adding one proton, you do the same for the electrons. I mean, that's kind of obvious, right? But it doesn't always go up in terms of energy by n equals 1, n equals 2, n equals 3. At some point, these energy levels the energy levels and the shape of the orbitals, they kind of mash and they go out of order. So we'll learn more about that tomorrow in our class. But anyway, they're giving you the order here. This is the way you've got to follow. Here's what I'm saying. An electron going in this hotel must go in here first. All right, go there, 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 go there. Oops, go there, go. It's just got to follow, right? Aufbau's principle says, lowest to highest, and it's already figured out the order for you. So this is a reference to use to answer the problems on the next page. So it says it tells you use the reference figures 1 and 2 from the previous pages to help you identify the 4 quantum numbers. All right, so it's already, we don't need that. All right, but the quantum numbers are labeled here for you on figure 1 and figure 2. So you can go back because you have your paper handout in front of you, I hope, and you've already done this before you're checking your answer. Okay, for that one electron, all right, the quantum number n is equal to, this is n equals 1, this is n equals 2, it's in the second energy level, right? So that's going to be 2. All right, L is going to equal, I'll do this in a different color. All right, L can have values starting from 0, so there's a 0, right? And this is your p orbitals, which are 1. And that's all you have because you go from 0 to n minus 1, and 2 minus 1 is 1. Right. So in other words, there's only your s orbitals and your p orbitals on the second floor of this hotel. Right. So you can say L is equal to p. Right. Now the technically correct answer is 1 because p orbitals are assigned the value of 1. I'll try to fit it both in here. All right, 1, and so that's your p orbital. Now the orientation here, you can say this is like x. I'll pick another color. So we'll go like x, y, z, right? Or to be more technically correct, this middle one's supposed to be z, but I don't really care that you know that. All right, so you would say that's in the y direction. This p orbital is in the y direction, and we can assign that positive 2. All right, actually, let me do this way. All right, so the technically correct answer is positive 2, and that's going to be in the y direction. Let me show you where I'm getting this from if you need the reference. So up here it tells you like, let me try to erase some of this stuff. You know what? I can't do that. So that electron was right here. Right, so you got n equals 2, L equals p, and the orientation is +1. All right, that hotel is facing like the parking lot, and this hotel is facing the beach, and this hotel is like has no windows. I don't know, so it's that kind of an analogy. Same room, right? Same cost. We call that degenerate rooms or degenerate orbitals. All right, the spin, it's spinning down, so we'll just do that. All right, so actually again the technical value would be like -1/2 or +1/2. All right, but be consistent. If this is spinning down, this one has got to be, -1/2 if you choose. All right, so just be consistent. It's pointing down. So let's do this a little faster for the second hotel. All right, n is, so that guy right there, n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. Right, so that's n equals to 4. All right, now this is going to be L is equal to 0. That's your s orbital. Now this is not your p, right? Because you have 5 of them. You can't have 5 p's. That's your d orbital, right? So that is L is equal to 2, and that's your d orbital. So that's going to be 2. Now you may be asking, like, why don't we have the p's? We'll get to that tomorrow. We have to learn a bit about the Aufbau principle tomorrow. All right, the direction. So let's do that in this green. All right, so this is -2, -1, 0, +1, positive 2. So it's facing the positive 1 direction. All right, and the spin is going up, and because I use positive for down arrow there, I'll just use negative 1/2 for the up arrow. Okay, this last hotel, this guy right there is in floor 1, 2, 3. Go back to my red. All right, 1, 2, 3. It's on the 4th floor. N is equal to 4. There's only one orientation of it, so you know that's your s orbital. That's your s orbital. That's L is equal to 0 is your s orbital. All right, there's only one way to go from negative L to positive L. L is 0. The orientation is 0. There's only one way you can orientate a s orbital. Oh, let me get back to my green for that. And then the spin is positive 1/2, so let's keep that consistent. Oh, I'm sorry, the spin is going up, so what did I say? That's negative 1/2. All right, spinning up. All right, doesn't matter. You can say up is positive 1/2. Just be consistent. All right, part 3, Hund's rule. All right, we want to maximize the number of unpaired electrons in degenerate orbitals. All right, are there any violations? There is. There's a violation right there. That guy, oh, not only that, oh, so there's a second part to it. Okay, so not only that, we have to have them spinning parallel to lower the energy cost of the system, of the atom. All right, so that should be pointing up. All right, or they all should be pointing down. Hotel B, I don't see anything wrong with that. All right, good. Hotel C, yeah, that's not a violation of Hund's rule. So I don't know, you circle that. I don't know. But we're going to circle it because it's violating another rule. Give me a hint. Right. It's violating Aufbau's principle, which is not a scientist. It's just a German word that means fill up. All right, but it's not violating Hund's rule, violating Aufbau's principle. Part 4 questions. How many rooms are on each floor? Really? Oh, S rooms. So there's only one S orbital at each energy level. There's only one and only ever one. And those are the ones that get filled first. How many p orbitals are there on the 2nd floor and higher? So p orbitals only exist at n equals 2 or greater. And when there are p orbitals there are 3 of them. Right? There's one in the x direction, the z direction, and the y direction. So there's 3 at every energy level available, starting from the 2nd and up. How many d orbitals are there on the 3rd floor and higher? So d orbitals are only available on the 3rd floor, or n equals 3, or higher, all the way out to infinity. So there's 5 of them. How many f's there are? 7 of them. How many electrons stay on the 1st floor? Only 2, because there is only one orbital available. That's the s orbital. All right, 2nd floor has, right, so 2nd floor has a s orbital, and it has 3 degenerate p orbitals. So you can put 2 in each orbital. And so 6 plus 2 is 8. We get the octet like that. 3rd floor is going to have an s orbital, 3 p's, and 5 d's. 2 electrons in each. Right? So you got 10 there, 6 there, 2 there, 18. What do the room numbers describe about each room? That's the orientation, or the way those orbitals are facing. M sub L. By the way, Hotel C above, what would be one reason to put the final electron in the 4s? It is in the 4s. This is a violation, but it's asking me if you can think of a reason for this violation to be acceptable. You could say, well, that doesn't happen, right? That's the 4s. But why would it do that instead of go down here where it should be? Well, you could say it gets its own orbital. So you'll increase the number of parallel spins, you can say. To get own hotel room, all right, you're going to pay a little more for that. Electrons are pretty stingy. They hate to pay extra energy to. All right, they get their own orbital. It gets. All right, and it will also increase the number of parallel. All right, so there are more electrons spinning in one direction. Parallel. All right, increased parallel spin. Draw a hotel for phosphorus. Phosphorus number 15. All right. Here's your 1s. Put 2 electrons in there. We need 13 more. 2s. You can use the figure, the reference there. Although on your test, you're not going to get that reference. You'll have to know how these fill. 2p. There's 3 of them. Hund's rule. All right, we got 10. We need 5 more. We need 3 more. All right. Now, the spacing here is obviously not drawn to scale in a real atom. Go back to page 1. No. Write the electron. No. All right, let's do it. Write. I should have just cut 9 out. All right, page 1. Write the electron configuration. That's not too bad. All right, so this is going to be lithium. Lithium has 3 electrons. It's going to be 1s2, right? That's right there. And then a 2s1, because there's only 1 electron there. All right, next one. That wasn't bad at all. All right, this one's got 2, 4, 6, 8. That's oxygen. Where's my? Oh. All right, oxygen. 1s orbital is full. 2s orbital is full. And then 2p, how we get to 8? It's got 4. 4. All right, last one. I got 2, 4, 6, 10, 12, 18, 19. There's a really fast way to do that, but I'll show you tomorrow. Oh, all right, 19. That's your, that's in the first column. That's potassium. So, okay, we got 19, 1s2. Done. 2s2. That's there. 2p6. 3s2. Right there. 3p. Now I'm going to run out of room. 6. 4s1. All right, again, if you're wondering why don't we go to 3D, we'll cover that tomorrow. There's got to cover Aufbau's rule. Let's do noble gas notation because we covered that in class today. All right, this is helium. So helium, put that in brackets. That's a noble gas, 2s1. All right, oxygen. This is your noble gas. That's helium. So it's going to be helium plus whatever's left is 2s2, 2p, 4. That's your noble gas notation. All right, potassium. It's going to be easy. All of that is a noble gas right before it is argon. So put argon in brackets, and then you have 4s1. That's noble gas notation for potassium.